Thanks. So yeah, this talk is, do read errors matter for DNA assembly? Unfortunately, you don't have to know anything about DNA or anything about assembly in order to follow this talk. It's just kind of a cute combinatorial problem I think that I became interested in over the last year, and so I figured I'd talk about that. Okay, so that's a read error. Yes, this is the illustration of the topic for today. Okay. Okay, and then I should mention that this is joint work with Ilan Shomaroni, who coincidentally gave a very similar talk last week. We didn't coordinate very well in advance, and David. Okay, so the general idea behind DNA assembly starts with DNA sequencing. And basically what you have is you have a very long sequence, which is unknown to you. And this guy is just composed of like A's, C's, T's, and G's. And current technology doesn't allow us to just read the bases off of this sequence directly. So basically what happens is you can imagine getting short fragments of this sequence. So maybe when I draw a box here, it means that I basically lift the string from down here, call this A, G, T, C, T. This would be like A, G, T, C, T. Okay, and I get a whole bunch of these short fragments, and these guys are called reads. And they come from basically random positions with respect to the original sequence, and I get a lot of them. Okay. So for the purposes of this talk, we'll just assume they are all the same length L. Okay. And I'll say in reads. Okay, so your goal is to take basically a basket filled with these reads, these short fragments, and then your goal is to somehow put them all together and try and determine what this underlying sequence is that would have generated these reads. Okay, so this sequence, just to give you an idea, length G, sorry, I probably can't see that over there. Okay, so the sequence of this, or the length of this underlying sequence here is G base pairs long. And so it's a really large jigsaw puzzle because G, even for bacteria, is something like order of millions of base pairs long. And for humans, it's, say, order of billions of base pairs long. So you get a whole bunch of reads of, say, length 200 base pairs or maybe a few thousand base pairs. And your goal is to assemble them completely. Okay, so there's kind of two ways of answering or trying to address this problem. And the first might be more from a computer science perspective that says, okay, so suppose I give you a whole bunch of these substrings. Give me an efficient algorithm for, say, producing the shortest superstring that contains all of them as substrings. Now, another way of looking at this problem is maybe more of an information theoretic viewpoint. Okay, so information theoretic question here. Might be of the form, for what values of n L can we unambiguously reconstruct this underlying sequence S? Okay, so actually quite a bit is known about this. In particular, if I think about plotting L and I'll call it the coverage depth, which is just n times L over G. So what is this? This is just the average number of times each base is covered, right? Okay, so you can come up with some pretty simple bounds here. So there's something called the Lander-Waterman coverage depth bound, which says that if these reads are taken at random positions, you basically need a certain number in order to guarantee that every single base is covered. If you don't do that, you have no prayer of reconstructing, right? Okay, and then in the other dimension, in the read length, there's another number here, which I'll leave as a mystery for this talk, but it's just a critical read length that depends on the sequence. The actual definition is not important for this talk, so I won't go into it. And basically above this, you can, or below this, you won't be able to reproduce the sequence. There will be two sequences where you could essentially shift parts around, and so there would be some ambiguity. And then we know actually from some recent work by Bresler, and Shea in 2013, they actually showed that empirically anyways, I mean, they have a proof of an upper bound and lower bound, and you can evaluate this curve for particular sequences. Empirically, the real line looks like this, where we can reconstruct and can't reconstruct down here.
Is that for random sequences?
No, so this is, okay, so let me give you the lay of the land here. So sequence model. So you could model this underlying sequence S here, and I think this is what your question was. You could model it as, say, an IID sequence or something like that. Or what you could do is you could take the, say, deterministic sequence or individual sequence model, where the sequence is just a given sequence. Okay, so this would be individual sequence model. And then maybe in this dimension, we could write read errors, question mark, and then no and yes. And basically, this is where this Bresler, Shea paper fits in. Okay, so that's this curve here for an individual sequence, but there's no errors in the reads. Basically, these fragments that are given to you have no ambiguity. I mean, they're taken directly from the underlying sequence. So there also is.
You are assuming that the reads land in random places, right?
Yeah. So that's what the assumption here is that basically the reads, you choose a position uniformly at random, and then the read is taken as that length L substring that follows.
So if all the reads consisted of repetitions of the same letter A,
Yeah.
then you wouldn't be able to reconstruct the length of the sequence.
Exactly. So actually, that's where this. Okay. So one assumption maybe that I glossed over here is we'll assume that this length of the underlying sequence is known. That's not realistic in practice, but in practice we actually have an estimate of how long the sequence might be. So just think that we know the length of the sequence, and we're trying to determine what exactly that sequence is. But you raise a good point that if a lot of my reads look the same, I mean, for instance, take L equals 1, in which case all of my reads are going to be A's, C's, G's, and T's. I'm certainly not going to be able to reproduce the sequence, right? I mean, we can agree on that point. So that's what this critical read length depends on, actually, is the repetition structure of this underlying sequence. And that's actually why it's important to consider the individual sequence model, because an IID sequence model has very short repeated sequences, right? So it turns out that that kind of the statistic that determines this critical read length depends on that repetition structure critically.
So what are the quantifiers? You can't really mean that it's with certainty you succeed.
No, so this is like a with high probability result, essentially. This.
With respect to this string's length? Or?
No. So in the individual sequence model, right, the sequence length is fixed, right? And so basically you're looking in the number of reads. So this is normalized, or basically coverage depth, right? And so as long as you get a certain amount of coverage, I mean, so if you take a random number or a number of reads, then you can guarantee that a certain fraction of the sequence will be covered with high probability, right? Or the whole sequence will be covered with high probability. So that's basically the with high probability
No,
context.
just with high probability, you need some parameter for.
Yeah. So your parameter.
I usually said with respect to n going to infinity. There's no n going to infinity.
No. So I agree. So I guess what basically this coverage depth would depend on, say, your error probability. Okay. Does that make sense? Right. Yeah. Okay.
Can you say what the individual sequence model is?
Yeah. So the individual sequence model is that this sequence, the underlying sequence which we're getting these reads from, is fixed. We don't know it, but it's just a fixed sequence. Okay, we don't make any stochastic assumptions about it. It's just a fixed sequence.
I see. So actually, following up on Dick's question, so I mean, what if there were just, you had all A's and then followed by all C's? I mean, could you?
Right. How could you hope to reproduce that sequence, right? Well, then certainly you would need a read length that's long enough to allow you to disambiguate kind of how long this repetition is, right? So if I have a sequence that's, we're getting a little bit far afield, but that's okay.
So does it mean the vertical dotted line will be more to the right?
It'll be more to the right. As I said, this depends on the repeat structure of the sequence. So here I can imagine like basically this set of C's is repeated here and it's also repeated here, right? So it's going to be very long. So it's going to demand that we have a very long read length, which will effectively bridge this whole string of C's in order to help us or guarantee that we'll be able to reproduce the sequence. Okay. So what I'm going to talk about today, though, is there's no with high probabilities, so that will satisfy your point. Okay. So let me just point out that there's a few other works here. The IID sequence model. So there's some work by Motahari, Bresler, and Shea, also in 13. Earlier, some work by Yukonin and Pevsner. Sorry, that's over here. It's like 91, I think, and 95. And then here is Motahari, Ramchandran, Shea, and Ma, also 13. And so today is here where we're considering individual sequence model, but with read errors. Okay. So let me now describe exactly the setting. So our setting, what we'll consider is a so-called dense read model. Basically what this means is I have...
Can you see if there is a better pen? It's starting to...
I have a read at every position. Okay, so basically I have my sequence S here. And my reads are just taken at every single position in this sequence. So I have G reads. And we assume that this sequence is cyclic. So to avoid edge effects, a read taken, say, at the very end here will wrap around and connect over there. Okay. Okay, so this is a dense read model. So what does this mean? It means we're operating way up in this regime here, right, where we just have maximum coverage. And so really this is kind of the regime that we're looking at. We're trying to determine this asymptote, essentially. Okay, now our error model. Is adversarial erasures at rate E over L. So what exactly does that mean? My read lengths are of length L. So what I'm going to allow an adversary to do is erase at most D positions per read. Okay. Something like this. So D erasures per read. And then there's another constraint here, which is if I look and I have a read at every single position, how many reads cover a single base in this underlying sequence? Exactly L, right? Right. And so what we also do is we restrict the adversary to put at most D erasures per base, right? So this is consistent with the error rate D over L. So D erasures per base. Okay, so that's the basic idea. So let me just introduce some notation here. RLS equals set of dense reads of length L. And then we'll just write R, say L, DS equals erased reads. So the basic picture is this, is that I have my sequence, goes through a sequencer, out comes my reads, then my adversary corrupts them, and what I'm left with at the end of the day is a whole bunch of reads with a whole bunch of erasures. And the question is, how can I assemble these to put them back together in a sequence? Is the setting clear to everybody? Okay. So actually, going through this, we realized that the question that we should be asking is not when can I reconstruct the original sequence, but what can I do in terms of correcting this set of reads. So this introduces the notion of, so this time is sometimes called the L spectrum. Because basically what it is it's the relative frequency of length L strings that are appearing in the sequence. So this introduces the notion of spectrum error correction. Basically what I'd like to do is take my corrupted set of reads, spectrum error correction, to produce an uncorrupted set of reads of shorter length. So if you can imagine, if my adversary is very lazy, right, and basically they take all the reads, and they always just delete the last D positions of them, then what I can do is I can take this corrupted spectrum, right, and I can produce an uncorrupted spectrum where L prime equals L minus D, for instance, because the last D are just erased, right? But that's only if I have a very lazy adversary. And so kind of the main result here is that we can actually do spectrum error correction even under this adversarial model. So let me write down the result. And I don't think I'll actually... is that if L so I need to define what this quantity is, but let me explain the result first and then I'll define exactly what it is. Then can correct So the only thing that I didn't define here is what exactly is this okay. which I'll tell you about in just a second. So what does this result say? Basically, it says that if my read, okay, so as a simple example, maybe set this aside for a second. So take K equals L crit. If L greater than Okay, so as a corollary, basically if I take K equals my critical read length that would be needed for the reconstruction in the error-free case, basically if my read length is greater than that critical length plus D times some multiplier here, which for now just think of it as a small number, it's going to be like 2, 3, then basically what I'm able to do is clean up that spectrum and then assemble the sequence. So let me define exactly what this M guy is. So as we discussed, the L critical is a function of kind of the repeats in the underlying sequence, right? So this M is actually another measure of kind of the repeat structure of this underlying sequence. So M S DL is defined to be the maximum number of repeats of Okay, so basically what I mean is I have my sequence S here. And if I look at, say, a bunch of subsequences, x2, x3, so on and so forth, and let's say that these guys aren't exactly alike, but maybe what the adversary could do is erase D positions from each of these and make them look like they came from some sequence X, right? So they aren't exact repeats, but they're D approximate in the sense that there's some centroid, and so basically it's you have these points, x1, x2, x3. And by D approximate repeats, I mean that they lie in a ball of radius D, right? So basically, what this does is it captures the approximate repeats, I guess. So this was slightly faster than I.
You don't insist that the segments were disjoint, they're just in the picture they're disjoint, right?
Right, just in the picture they're disjoint. They could be actually overlapping. So I just want to give kind of the idea of how this works. So actually, there's less time than I thought there was, which made me rush through quite quickly. I think I got a little bit out of order here. Okay, so basically, how does this work? So what I want to do is I want to show that if let's say what I do is I take these erased reads and I assemble them into some sequence S hat. Right, so this basically is, I built this by putting all these erased reads on here. Okay. Maybe these guys have some erasures in them, but what I'm able to do is, depending on how they align, I correct and build a sequence S hat. So if I want to show the spectrum error correction result, what I need to show is that basically if these guys are of length L, every sequence of length k plus 1 that appears in my reconstructed sequence should also appear in my original sequence, right? Okay. And so basically what this corresponds to is if I think about listing all the subsequences of length k substrings of length k plus 1 in S hat. So let's say S hat 1 up to k plus 1, S hat 2 up to k plus 2, so on and so forth. For the bipartite graph here. And I list all the substrings of length k plus 1 in S. And in this bipartite graph, I connect vertices if they're equal, right? And the first thing that we notice is that this bipartite graph, any connected component is a completely connected component, right? Because if this equals this, equals this, equals this, well, clearly that also has to be equal, right? So in order to show this result that basically the k plus 1 spectrum of the sequence I reproduced equals the k plus 1 spectrum of this original sequence, corresponds to just showing that there's a perfect matching in each of these connected components, right? So for that, it's just essentially Hall's theorem. Okay. And so the basic idea behind this, you can probably see how it goes. Is we just basically follow our nose and use the properties that we have here, and we say, okay, well, let's look at where all these reads go. Let's say this read originally came from here in S, and maybe this read also came from here in S, and then this read maybe came from here, and this read came from over here. And all I need to do is look at basically where this section is in each of these guys. So that's there. This guy is maybe here. This guy, let's say, is here. And if I call this sequence X, this X1, X2, so on and so forth, up to Xm, well, by the constraint on the adversary, right, that I can erase at most d positions, these guys are all within distance d of this X. Yeah, so basically there's at most ms dl of these guys, or k plus 1, sorry. And now, how many reads cover this sequence? So each read is of length L. The length of X is k plus 1. So basically there's L minus k reads that completely contain this guy, which by that inequality is greater than d times ms. dk plus 1, right? So just by pigeonhole principle, now there's got to be at least one of these guys that has greater than d reads sitting on him. And by that kind of vertical constraint on my adversary, it allows me to completely correct all those errors, right? So that's the case A equals 1. And then the other case requires, or more generally, it's the same. It just requires more bookkeeping. But basically, kind of, for us anyway, it was kind of interesting to think of, instead of trying to do error correction and reconstruct the whole sequence, really what we can always do is just kind of, abandon, really, trying to reconstruct the sequence. And we can always reconstruct a smaller spectrum that's completely error-free. And so it kind of makes sense if you think in the extreme case, I can always reconstruct the one spectrum. It's just A's, C's, G's, and T's, essentially. But then for like larger K, right, it's non-trivial. And so a few things about tightness. In fact, we don't know how tight this would be in general, but we do have examples where this is tight, where we can construct sequences that this is the best that you can do. And then, as I said, we evaluated this guy for several real genomes, and it turns out to be a relatively small multiplier. So really, do read errors affect DNA assembly? And the answer is, well, you increase your read length by maybe 50% in the worst case, but it's not like an order of magnitude blow up or anything like that. So another thing that kind of comes out of this is presently in practice, the way that error correction is done in assembly is it's kind of a separation-based approach, as an information theorist would say. Basically what they do is they cluster all the reads and then they try to do error correction that way. So then they assemble based on kind of the assumption that they have a clean set of reads. Whereas here, it's not a constructive scheme because we don't tell you how you should assemble these erased reads. But what it's saying is that you should do kind of the error correction and the assembly jointly. So one final comment. If we do, okay, so we might say now that there is some, okay, if L greater than min, K greater than S. Okay, so this guy maybe we might call L tilde critical. So if my read length exceeds this guy, then I'm guaranteed to be able to reconstruct a sequence. But it's a little bit funky if you think about it, because it says that my read length needs to be longer than some function of the sequence that I don't have, right? But actually it's not too hard to see that there's an implied certificate property here, that if I reconstruct S hat, say, and L is greater than L crit, which I can compute because I basically constructed this guy, then S equals S hat. So basically you can do your sequencing, assemble, and then check and certify whether you got the correct answer or not. And this is all under like adversarial errors and whatnot as well. So that's it.
Questions?
Do you have anything under real errors, no deletion, but changing letters?
Yeah, so actually we believe that just kind of like similar to a coding theory type of result where you can handle substitution errors at like half the rate of erasures, we believe that you should basically just stick a 2 here for substitution errors. In fact, we thought we had a proof of that, but then we found a small bug. But we believe that it should still hold, and we think that we can actually resolve what we have. So, yes, not yet. I can't say anything formally on the record, but I believe that it works out to be essentially the same. The real problem is that in sequencing, the types of errors that are predominant are not necessarily substitutions or erasures, but insertions and deletions, which are kind of a whole nother animal. So, I mean, the good news is that very little has been done on the theoretical side of sequencing in the presence of errors. So erasures is kind of a very first step, but certainly we have kind of a long way to go. But I think it's more about trying to get intuition about whether the errors significantly affect the read length required or not. Yeah.
How essential is to have a number of erasures per read and per page the same? I mean,
It's not essential. So actually, you could put, things would change slightly. I think if you said like D errors per read and then say D1 errors per read and then D2 errors per column, then one of these becomes D1 and one becomes D2, I think, and that's it. But the basic idea is that we have like a erasure rate of D over L. The idea is to try and somehow model random errors, right, which you would expect would happen at kind of a uniform rate. We have a different model where we consider like windowed errors. So any window of a particular length only contains a certain number of erasures, and then this actually becomes much better. This is pretty pessimistic.
More questions?
Okay, let's thank Tom and another speaker again.